So it's my pleasure to introduce Professor Wei-Yin of the University of Wisconsin. He's originally from Singapore.
Yes.
Got his
British colony.
British colony, yeah. Former British colony, former. He got his BSc there and his MSc there, and then he went to Berkeley, California. We're not in. Well, it is an ex-British colony, or ex-British 13 colonies. Berkeley, California. That was never British. No, that was never British. Okay, so Berkeley, PhD from there, and he's been working in Wisconsin for several decades. 4 decades, and he's a master of classification and regression trees and forests, upon which he's been working for many decades. Thank you very much.
Thanks, Sean. Well, thanks, Sean, for giving me the chance to speak here. Like Sean said, I've been working on this topic from the time the topic first became into the forefront, the CART method, if you heard of that, C-A-R-T, by Bryman, Friedman, Ocean, and Stone. In 1984, they published that book, and about that year, I got a flyer saying that if I adopt that book for a class, I get a free copy. And so I wanted a free copy, and I volunteered to teach from that book. And then as I taught from the book, I had to really study it because I have to teach the students. And then I found a lot of problems with the algorithm. And then I found some ways to get around it, and it keeps going. And the whole thing has been, when I first did it, it's just called multivariate analysis. But then it became machine learning. Now it becomes AI. So this has something to do with explainable AI, which I won't have time to talk about, but the regression trees are methods, you can call them AI methods that are explainable, obviously. Okay, but today I'm going to talk about something which got me very interested in about 10 years ago when I visited the Bureau of Statistics at Washington, D.C., because I have a way to deal with missing data using regression trees, and they wanted me to visit there for a summer or two and apply my methods to census data. And that's when I really encountered really messy data with lots of missing data. And so I've been thinking about how to solve this problem. And now missing data is actually very strange. Many years ago, there was a big deal about big data. Then it became machine learning. Now it became AI. Nobody talks about missing data. We don't have a single course on missing data in Wisconsin, not at undergraduate level, not at the graduate level. When I was at Berkeley, nobody talked about missing data. But missing data is, if you work with real data, they're everywhere. So why is it that nobody talks about missing data? Nobody does research about missing data. Why? I think part of the reason is because in the 1960s, Don Rubin came up with this fantastic idea that became multiple imputation, right? And it is a very beautiful theory. It's a Bayesian theory. So there are theorems. Sean was just talking about theorems, and you want to get papers published, at least in the old days, you have to prove theorems, right? So here's this theorem that justifies multiple imputation. And then it became very popular. This multiple imputation method is in all kinds of software. It's in SPSS, SAS, R, Stata, everywhere. So when I work with collaborators, like in Wisconsin, whenever they have data, they will say, let's use multiple imputation and be done with it. It's like, you don't have to worry, just send it to the cleaners, comes back clean. Right? And so as a result, I think researchers, first of all, researchers don't really, they're not excited about it because and this is including me, I thought the whole problem has been solved. Until I went to the BLS, the Bureau of Statistics, and I found that those methods, those algorithms won't work. when you have too many variables missing data, okay, they keep crashing. So even if you want to use those methods, even if the algorithms are commercialized, right, you can't do that. And the people at the Bureau of Labor Statistics, the people at Census Bureau also don't use them. Okay. But in universities, like maybe in Cambridge, they are very popular among scientists because it's so easy. Just click a button and everything is clean. But when you have really messy data, then the programs just keep crashing. So I'll mention something like that to you. So today I'm going to show you a different way of doing this. So I'll illustrate with one example from COVID. So during COVID, the 3 years, I was invited to join a group that was funded by the National Institute of Health, the National Cancer Institute. They were interested to see whether cancer is a predictor of death from COVID. So, and because the University of Wisconsin already has in place a data center for years, where we draw all the data, all the cancer data from all over the United States, and they deposit it in Wisconsin. So we already have the infrastructure with the matter of pulling them. So we kept getting monthly data from all these. There are 21 healthcare systems. A healthcare system is not just one hospital; it could be a huge, like some of the New York City hospitals. So this is the data I'm talking about. I will talk about is about halfway through that 2-year period. So my data has 85,000, almost 86,000 patients. They were hospitalized for COVID, and so we want to know how many of them either died or had to be intubated. At first, we want to analyze just people who died, but then the death rate is too low. So we just make it a little bit more, so including, because if you get intubated, you're actually seriously ill, right? So MI stands for mortality or intubation. So it's a 0-1 outcome variable. We have 30 predictive variables. Actually, we have hundreds of predictive variables, but some predictive variables are not useful from a scientific point of view for predicting death. So like if you're already, like you can't breathe, right? You can't breathe is different from whether you have cancer. It's not comorbidity. You can't breathe means at that moment you're already dying. So you use that to like sepsis. Sepsis is an excellent predictor. But if you're a doctor, you know, of course, if you have sepsis, you're not likely to survive, right? So that would beat any kind of comorbidity if at the time you're admitted you have sepsis. So we throw out all this. So the primary goal is to try to find a model that will suggest what is likely to cause you to die or be intubated. So this is just a summary from R of the data. So about 18% for the proportion of but I'm thinking of people online. The point is that they will not see me. So 18% is the average. I would call it death rate, but it actually includes intubation. Sex is about even. Age is 18 to 90. BMI. So remember, we have 85,000 people. So about 5,000 we don't have BMI. Race. NAs are the missing values. Ethnicity 10,000 missing. Blood type 51,000. Rh factor. Rh factor is rhesus factor. There's plus or minus. There's no such as a blood type. Apparently, most people have positive blood type. And smoking status. So this is a variable that was most greatest interest to my group, because my group are smoking cessation researchers, and they have been funded by because smoking has to do with lung cancer, so they've been getting all their grants from National Cancer Institute. So they were most interested in whether smoking status is a predictor or not. And asthma, COPD, bronchitis, bronchial, I don't even know how to pronounce this, diabetes, cardiovascular, renal disease. And so a lot of comorbidities cancer as well, pregnancy, A1C. Right? So, so there are a lot of missing, so this is proportion of missingness. The biggest is A1C, that's blood sugar. So it goes up to almost 80% of people with A1C. These are 3-year look back data. So these are electronic health records. So they go into the hospital, each hospital, look at the electronic health records, look up 3 years, right? If there's any mention of cancer, then means the person has had cancer before, right? Those of you who have worked with HR data may start to wonder why we have so many missing data on these 3 variables. So these are the patterns of missingness. The biggest, this is the proportion at bottom. Blood type and RH factor, which is a blood test, is the most missing. Okay, so now what do? If you're a traditionalist, you don't know about multiple imputation, you say, why don't you just do the simplest imputation? Impute the mean and the mode for categorical variables, mean with continuous or ordinal variables. If you're missing an age, you impute the mean age, right? Then you can fit logistic regression, because it is standard logistic regression, 0, 1. And in fact, of the thousands or tens of thousands of papers published in COVID in 3 years, 99% are logistic regression. And many of them don't mention about what they did with missing data. Well, people don't even wonder about it, just look at the logistic regression results. So if you look at the logistic regression, these are the p-values, and they are very significant because we have 85,000 people, right? A positive coefficient means that you're more likely to succumb. Okay, so males are more likely to succumb to COVID. Age is positive, so the older you are, the more likely. We all know that, right? So, everything. This is not so. Smoking status is not so exciting for my collaborators because it's not significant. Right? So everything looks fine except those in red. So this is the second part of that output. Pregnant has a negative sign. Positive sign means it's more risky if you have that value. So this says that if you're pregnant, you're protected a little bit. I don't know whether this is a fact now. I don't know. Cancer cannot be a fact. It says cancer is protective. It's negative sign. It's very significant. Right? Hypertension, if you have hypertension, it's good for you. Mild hypertension, so depression, yes. Anxiety, yes. You believe that? Right. It doesn't make sense at all. So what's the problem? Problem data? No. Data, real data. It's not sample size, a lot of data. Is the problem logistic regression? Could be. Right. So that's a problem with interpreting this kind of parametric models. Right. If you have some sort of multicollinearity, you get crazy kinds of things. What people do, I think, is that when they do this, then they throw away some of these variables and refit until things come up sensible. Well, it could be the imputation that's wrong, right? Because we just use a dumb method. So let's try multiple imputation, state of the art, right? This was a paper published by Rubin in 1987. I think this is a book. This paper was in the 1960s. So what does multiple imputation do? So you have a spreadsheet with missing values. You fill them all with means and modes. Really. You take one column at a time, do it as a Y column, and do a regression on all the other columns. Right, so there's no missing data there. Everything is filled up. Right. If the Y column is a 0, 1 logistic regression, you fit the logistic regression model. You get the predicted values, right? And then you fill in the missing values in that column with the predicted values. And then you go to the next column. The next column is age, continuous variable, you fit the linear regression model, right? And you get the fitted values for age, and you replace the initial values with this outdated. It makes a lot of sense, right? And you go through it 5 to 20 times. One time, when computers were slow, they would say 5 times would be enough. Then computers became faster. They say, oh, maybe 20 times. Now they say maybe don't go to 20 times because it doesn't converge. Okay, so now the conventional wisdom is don't push too hard. All right. So, all right. And that software implementation is the most famous is mice, multiple imputation by chain equation. Right, there's a book. This is the original paper. So let's do logistic regression with mice. So now it's not a dumb method. Now it's really state of the art. First page, all makes sense. Second page, you would think is I copied this from the previous one. It's the same thing. If you're pregnant, it's protective. If you have cancer, it's protective. Right? If you have hypertension, it's protective. Depression, basically the results are the same. So it's not the fault of the imputation. I think the fault is logistic regression. Now, if that's the problem, but how do you fix this? You throw in interaction terms. Now that's harder to interpret because you have interaction between cancer and something, cancer by itself, that's something by itself, right? It becomes really hard. In fact, in my experience, in medical papers, or scientific papers, very few will fit a logistic regression model with interaction terms. Not because they cannot do it, because it's very hard to interpret. So the real lovely thing about logistic regression or linear regression is because you don't have interaction terms, things are supposedly very clear cut until you see something like this. So, well, this is something I took from the book by Van Buren, who wrote the book on mice. And it's interesting what he wrote. This algorithm is univariate optimal, but not necessarily multivariate not optimal. But that assume this cycling, right? So there's no clear theoretical rationale for convergence of the multivariate algorithm. The main justification is through simulation studies. I don't think there will ever be a theorem. It's too complicated. Everything based on simulation studies, I don't know how extensive that was. Another danger occurs with the imputation model is so-called uncongenial. Uncongeniality can occur if the imputation model, the model you use to do the imputation, is more restrictive than the complete data model. The complete data model was the original model before things became missing. Right? So your complete data model may have interaction effects you don't know, but that's a real natural model. Now you fit a logistic regression to do patient, then that is a more restrictive model. So that's called uncongenial. And if that happens, then you can introduce bias and possibly inefficient estimates, right? I don't know why people care so much about bias. In traditional statistics, they care so much about bias. If the model is not linear and has interaction terms, the slopes don't mean anything. The slopes don't exist. If you have a parabola and you fit a straight line, you're estimating a slope, but the parabola has no slopes. And you talk about the bias. Bias is what? Expected value of the estimator minus the truth, but the truth doesn't exist. Right? So I'm not so hung up about, I'm a more non-parametric person, so I don't care too much about bias. You care about bias only if you really know what a true model is. Okay. So I mentioned about CART. So this is the granddaddy. I apply CART. It's so simple. On the other hand, it's so darn simple. It just says only age is important, right? So 18.18 is the percentage of people who succumb to COVID at the root node. And then if age is less than 56, less than or equal to 55, you go to the left, and the response rate is 11, right? So down from 18 to 11. 35% of the data came here and 65% went there, right? So, and this, you don't need CART, you don't need anything. You just do univariate analysis, right? Do a two-sample t-test or something, you'll find the age is significant. The only thing is maybe CART gives you the cut point. If you do a t-test just on age and COVID, MI, right? You see the significant, but you don't know where to cut it. So So CART is obviously very interpretable here, but it's quite useless. Then I use something more fanciful called conditional inference tree. This is our package C tree. Oh, it's so big. So anybody who tells me regression trees are easy to interpret haven't really used them. Okay. I mean, it's so big I can't even print them. I try to stretch and so forth. I just can't. I mean, but age is still up there, the first one. And then it's sex and hypertension and so forth. But luckily, I could print out the text version of the tree. But then you can see the rate again, right? If there is no hypertension, then let me see. No hypertension, 0.3. Oh, yes, hypertension. Let me see, what is it trying to predict? It's trying to predict no hypertension. What is trying to predict that rate? So maybe this is okay. I thought this is the opposite. Hypertension must be. Fortunately, I can't see what this is. Cancer, no cancer. This, sorry, this is death rate. So no cancer is 13.9%. With cancer, the death rate is 5.5%. So it's consistent with the logistic regression model. So no hypertension. Yeah, if you have no hypertension, your death rate is 31%. If you have hypertension, it's protective, 20%. Right? So we see the same kind of issues. Cancer. No cancer, your death rate is 28%. Baseline is 18%. But if you don't have cancer, your death rate goes up to 28%. Your cancer is 22%. Right? But these are not marginal. These are in this tree. Right? So how did these methods handle missing data? What CART does is it uses surrogate splits. So if you have a split that is missing age, so it finds this split based on age by looking at all the observations that you have age and find the best cut. And then if you have a person who is missing age, then the person will be sent either right or left using some other variable, a surrogate variable that is most highly correlated with age. And then if that variable says you go to the left, then you go to the left, right? But then the surrogate variable may also have missing values, and you go to the next surrogate. So you can't really predict if somebody is missing age, where it goes, because it depends on what is the first surrogate, and if that is missing, what is second surrogate. So it's not explicit. You know that it can handle missing data, but it's not clear. Even if I tell you how it handles, you don't know on a case-by-case basis where that person goes, because it depends on the availability of the surrogate splits. For C3, it just goes randomly. The default is just toss a coin. That's even less explicit. Right? Okay, so you have somebody missing age there, you just flip a coin, you go left or right. So the main point here is it doesn't show you exactly how missing values are handled. Okay, so the guide method that the first paper I wrote in 1988, for my daughter was right after my daughter was born. It was actually worked before she was born. So one of the biggest things that in that original 88 paper was unbiased variable selection. You see, in the CART method, the first split was on age. How did it select age? It looks at the best split for age, best split on sex, best split on cancer, best split on BMI, and so forth, and gets the best of the best. That causes a selection bias. Because for sex, there's only one way to split the data, male or female. For age, there's so many ways to cut. All things being equal, age will be selected. So what that was corrected in 1988 was to first select the variable, then select the split point. And actually, this has a lot of benefits from computational point of view. Once I select the variable, then I find the best split point. I don't have to find the best split point for every one of those variables and waste all my computer time and throw them away just to find the best one, right? And the second thing is the missing values, right? So if x is an ordinal variable at age and it has a missing value, I call it NA, it will consider a split that only puts missing values to one side and not missing. That's one possible split point. Another split point is consider all those that are younger than some age less than some x, like 50, like 52. And those that are missing go to the right, okay? And the inequality with asterisk means the missing go to the left. So here, when you see an asterisk, it says, as I put in yellow, missing values will go to the left. So if I have an inequality that says x, age less than or equal to with an asterisk 55, it means that if age is less than or equal to 55, you go to the left, or if age is missing, you go to the left. But if the split was this one in the middle, and if it's still age less than or equal to 55, it means that missing values go to the right. So the asterisk is the indicator that that's where you drop down the tree. Okay. For categorical variable like sex or whatever, we just treat missing as a new level, so that's not a problem. So I forgot to say, why do we need to do missing value imputation? Because if you want to fit logistic regression, right, a missing value on an ordinal variable or continuous variable cannot be left as qualitatively missing. It has to be a number, like age, because age is a predictive variable. So you have to replace it with a number. But if you have sex or race, you can just have another dummy variable. So 0, 1, you know. So for logistic regression, if your categorical variable has missing values, you can just create a new category for it. But you can't play that game with a continuous variable. So this is my guide tree. It's not too long, not too short. The first split is exactly the same as the other two methods, age less than or equal to 55. But because the less than or equal to 55 does not have an asterisk, it means the missing values will go to the left. Although in this example, everybody has an age. There's no observation of missing values. Okay. But you can still use this tree for a new patient. Now, I circled, first of all, let me tell you about the colors. Okay. I have yellow at the terminal nodes, I have yellow and blue. Yellow means the death rate is above the grand average, 18%. So this helps you to see where people are dying more, where are the yellows, right? Yellow is bad news. And blue is good news. So you see most of the blues on the left. The left are where the young people, age less than or equal to 55. And when it's on the left, when you have young people, there's not much going on. It stops. Actually, it doesn't stop. It grows a very tall tree until down to the ground floor and then prunes it up. Okay, so that's yellow and blue. The red is very interesting. Whatever your age, smoking status is the next most important. So smoking researchers are very excited. Smoking. But the split is on what? On whether we know your smoking status or not. It's not whether you are a current smoker, former smoker, or never smoker. Those are the three words. But it's on whether you have, whether we know or we don't know whether you smoke. Okay, so let's look at the left there. If we don't know your smoking status, then you come in here and it's RH factor, rhesus factor. There's something to blood, right? It says also NA. If we don't know your smoking status and we don't know your rhesus factor, your death rate is 18%, which is about baseline. But if we don't know your smoking status, but we know your rhesus factor, it jumps up to 41%. Everybody has a rhesus factor, right? It's whether we know or not. How come, if we don't know, you're more likely to survive? If we know, yes.
Because you're only testing the people, you're only testing their rhesus level if they're really, really ill and they're more likely to die.
Yeah, you hit it exactly right. See, we forget this is COVID data. Even though we're looking at 3-year look back, there are many patients who have never been to the hospital. Because in the United States, the emergency room has to treat you, whether you have insurance or not. All right? And this is a time when the hospitals are all overflowing. People are sleeping on the floor. So if you don't know your rhesus factor, means we never took your blood. Right? We never took your blood. So this says if you don't know your rhesus factor, that means we never took your blood. You're probably more healthy. You're probably more healthy. If we took your blood, that means they need to find out what's wrong with you. 41% will die. But that is for people who we don't know smoking. What are people who we know smoking? Let's look at the bottom of this. These are the death rates, right? 11%, 19%, 4%. They're all smaller than over here. Okay. So if we know your smoking status, never mind whether it's a smoker, current smoker, never smoker, or former smoker. If we know that, then you're more likely to survive. The death rates are lower than here. If we don't know your smoking status, you're more likely to die, regardless of rhesus factor. Who are the people we don't know the smoking status? They cannot talk. They cannot even breathe. There's no chance for the doctor and nurse ask, have you ever smoked? In a normal patient visit, annual visit, right? They would go through all these things. But it's an emergency. Okay, that people are unconscious and they have never been to the hospital. They have no hospital records. You never know. Right? So this is something that if you use any imputation method, you'll never see this because it's hidden. It's hidden. I showed you the logistic regression models. There's no such thing as smoking missing because it's all imputed. So here, smoking status is a very good predictor, but not because you are smoking or not smoking. Because not knowing your smoking status is a measure of disease severity. We are trying to predict disease severity, death, intubation. Not knowing your smoking status. Not smoking status, but not knowing your smoking status. Knowing or not knowing. It's a very good predictor of severity of disease. So here's an example where you should not do imputation. And this only, as I note, it's the only method that will reveal that to you because we don't. Couldn't we just do it any normal?
No. We've had problems in the past with people coming in who shouldn't have been in and then disrupting the seminar.
All right. So these are important scores. There are a lot of methods nowadays that give important scores. The most important, the longer the more important age, then smoking status, but it's not smoking per se. It's whether we know whether it's smoking, and we know smoking or not. And I may say that there are many methods that give you important scores. I'm sure some of you have used that. But Guide is the only one that gives confidence levels. There are many machine learning methods that we can rank the variables in order of importance. They can give you the score, but there is no idea whether this. You can have a bunch of noisy data and you can still have the important scores. But I don't have time to talk about this here. This is from random forest, so I'm going to skip that. So I'm going to jump to the next example. This is where I spent 2 summers about 10 years or so ago. The Consumer Expenditure Survey is something that the US government does every quarterly. It's a very complicated survey. Every quarter, they rotate out 1/3 of the respondents. They put in 1/3 fresh ones. They want to have some continuation, carry over from quarter to quarter. So once you are in there, you go there for 4 quarters and you rotate out. So, but I'm just going to analyze it from one cross-section and one time point. So my data set has about 4,000. A consumer unit is a household, CU. And we have about 4,000, and we're interested. So when I went to the BLS, I asked them, what should I use as my response? They said, oh, try this. Amount of interest and dividends you received the previous year, INTRVX. So our goal was to estimate the national mean. But about 1/3 of them in data are missing that variable, right? So we want to estimate a population mean, but we only have data on 2/3. There are 550 variables after deleting all the other variables. And about 20% of the variables have some missing values. 12% have more than 95% missing. When I wrote this paper, one of the referees was saying, who would include a variable with more than 95% missing? And my response was, because I can. I mean, if you don't, what about 90%? What about 85%? Well, where do you cut it off, right? People don't include it because they don't know, or they worry that imputation will cause problems. So, but the good thing with the guide is you just tell the guide what is the missing value code, and it will handle everything and draw you a nice picture. So here's a histogram of the response variable, the missing, non-missing Y's, the interest and dividends. Most people have very little money, interest and dividends, but there's some millionaires, so a lot. Okay, so these are some summaries. There are 550 variables. I cannot show you all of them. But the first thing that struck me was age of spouse. Why 44% of the sample are missing this value, age of spouse? The age of respondent to the survey, there's no missing values because it's an in-person interview. You forget, they ask you for your passport or whatever, birth certificate, and pick it out, right? 44% of them don't tell you the age of their spouse. And I was wondering, are these people who marry very older, much older or much younger spouse, they're embarrassed? They think, why 44%? This seems to be everywhere, every country. Yes.
People who aren't married.
Yeah, they're single.
Yeah.
They're not married. Now you bring up multiple imputation. You want to use age of spouse as a predictor variable in a linear model or logistic regression model. You either throw away this 44% of the data, or you want to use it, you impute it. You're imputing something that doesn't exist. After imputation, your sample is completely different from your population. So multiple imputation is very convenient, one click. SPSS or whatever, right? But it's just one shot. Oh, by the way, I forgot about something I want to tell you.
Is marital status not one of the variables?
Sorry?
Marital status.
It is also, it is, yeah. So if you are smart, but if you are not smart, that's why the government, the US government, pays a lot, thousands of dollars, hundreds of thousands of dollars to these consulting companies. They're all in DC. They analyze all this census data because they have very specialized, tailor-made programs to analyze it, specific for each survey. And they spend years to tailor it. Right? But before I go on, go back to so I asked you why those who have worked in AHR data, why there are so many missing values? That we all know, right? Because now we know, because some of these patients are brand new patients if we don't have data, right? But if you have worked in EHR data, you would also be surprised that for these comorbidities, we have a lot of comorbidity and no missing values, all the diseases. If you had worked with EHR data, you won't believe this, right? Can you believe 85,000, almost 86,000 patients, we know everything about their comorbidity, whether they have it or not. Can you believe it? You wouldn't believe it. So why is it in this data set, there are no missing values?
It's okay, there's no.
Yes, because the doctor imputed it for me. The doctor who asked for this data, told the technicians all across the United States, if that's missing, code as no. Now we don't know. We will never know. If he had left it as missing, I can decide to impute it. You can decide to impute it if you want. At least you know which cases you are imputing. But somebody imputed it for you. He's not using mice. It's just judgment. So that's a result. This data set is useless. You will never find that any comorbidity is predictive of COVID. Because it's corrupted. And the NIH spent a lot of money to collect this. They were supposed to keep it for future generations to analyze. I don't want to touch this data set. It's another example of imputation. So be careful as a statistician. If you have some control, beg the investigator not to do anything to. Anything, you can do it, right? You can do whatever you want. So age of spouse, 44% missing. Now I put some things in red and blue, blue and then followed by red. The blue one is, did you have any credit cards, including store cards and gas cards 1 year ago? Yes or no, right? If yes, you answer the next two questions. If no, it's missing. These are called skip questions. If it's irrelevant, it's missing. If you don't know that, you impute. So a person who had never had any store cards, you impute, suddenly has answers to the two red questions. It's very difficult to handle for ordinary statistician. You really need to go and read the survey questionnaire. You need to know which question is a skip question. That's why there are hundreds of thousands of dollars the US government, I'm sure the UK government, to pay to consulting companies, statistical consulting. Their job is to understand the survey, and they use the same thing to analyze it year after year. I asked some of these people what they do. They say, oh, like the age missing. Oh, they fit separate models. One model to those people who tell you the age of spouse, and one model separately to people who don't give you the age of spouse. But some of the people who don't give you the age of spouse are not necessarily single. They just don't want to tell you. Right? So now you see a separate model. That model includes a mixture of people. And then now you have these things. So now you fit separate model. You run out of data. Right? So, and then 99% missing. Because the easy solution is to throw it away. But we are interested in predicting the amount of interest and dividends. That's a financial outcome. These are financial variables. Right? So they're 99% missing. Hispanic origin of spouse, 98% missing. Some of them are not married, some of them don't tell you, whatever. Liquidity, the first question is, do you have any checking, savings, money, market accounts, or CDs? Yes or no? No means the next 4 questions or 5 questions is NA, missing. So you need to know they're connected. You know there's a skip question. Otherwise, you start imputing everything. Right? And then your data set will no longer look like the population. And they're all high proportions are missing, 97% and so forth. Right? The next one is, did you have any other debt, such as medical loans or personal loans 1 year ago? Most people, I would say no, but there's 99% of people don't tell you. More than 99% left missing. Sometimes when you're in the questionnaire design, you're doing a questionnaire design, you want to extract as much information as possible from the respondent. But it's tiring for the respondent to answer all these questions. So you have to balance that. Because if you make questions too long, they just give you garbage or they just stop answering the question, right? And you get all this missing. They're not missing at random because the respondent just quit. This is retirement survival benefits. Yes or no, and then if it's no, next question will be irrelevant. All this. Yeah. But one thing that's different from the BLS data is that for every variable that has missing data, it's coded as missing, but it gives you a reason why it's missing. So if X is age of spouse, right? So you have the actual values, and then if it's missing, it is missing. But then they have another variable called age of spouse underscore. That's a flag. And that flag takes one of these 5 letters. A means it's valid and missing. You don't have a spouse. So it explains why that's missing. B means it is invalid. Okay, in this case, it's probably not relevant, but if age of spouse, minus 10. How can age of spouse is minus 10? That's called change to missing and with the B code. Another one is don't load. This is the one that they refuse to answer. That's a C code. And then D is when it's a valid data type. T is a top coder. Right? For privacy reasons, anybody in the top 3 percentile of every column will be changed to the average of the top 3 percentile. Say for example, age, right? If you're 105, they don't want to reveal 105 because it's easier to figure out who that person is. And because it's easier to figure out that person, who that person is, that person will not respond. So they want to get as many people to respond as possible to protect you. Right? So if you're 105, you'll probably be rounded up to 91 or 92. That's top coding. Now, top coding would also play games with logistic regression and linear regression. But for regression trees, if the split is on 55, we don't care whether you're 105 or not. You're on the right side of 55. Right? Doesn't matter. So these are the kind of splits that you see in the guide tree. The first one we've seen before. They always check whether missingness alone is predictive, as we saw in the smoking status example. And so these three we've seen before, but it also can split on the missing value flag. Right? It could be that the missing value flag for age of spouse is A. That means it's validly missing. And we know that those people don't have spouses. So you have these 5 types of splits. And now, okay, now we go back to the original goal of trying to estimate the population mean. We have 3 methods, basically 2 methods. The first is to impute the missing values, right? And because the Y here is interest and dividends, okay, it's okay to impute it. So you fit some model, some regression model, and there's some sampling weights because it's a nested sampling kind of situation. So you multiply by the weights and divide by the total weights. So you need to get the Y hat for the 1/3 of the data where we do not know the interest and dividends. You use the 2/3 to predict the 1/3 and give it a Y hat. The other one is inverse probability weighting. Many of you may know, right? We upweight those responses with that pi. The pi is a propensity score, the probability that somebody will give a response, right? But that requires you to estimate pi. So you either estimate Y in the first method or you estimate pi in the second method. Then the third method is called doubly robust estimate, which is basically using the first method and then take the residuals from the first method and use the inverse probability weighting method. Right? These are standard methods in sample survey analysis. So we'll just do that. So I show you 2 trees. 1 tree to estimate Y hat and 1 tree to estimate pi. So this is the tree to estimate Y hat. So here's a tree, you predict Y by dropping the observation down, and wherever it drops down, so like at the bottom here, the bottom yellow node, there are 2 numbers, one in italics. The number in italics is a sample size, only 44 observations from there. And the average interest and dividends for the 44 is $46,000. Okay. And then you see here in the red, H2 less than or equal to 56 with an asterisk. That means if you end up in this node on H2, and if each spouse is missing, go to the left. So these are the people who go to the left are people who are not too old. They are at most 56 years old. Sorry, age of spouse is not too old, right? At most 56, or they don't have a spouse. Okay. And there are 156 of those people, and the average interest and dividends is $8,000. So if you compare these bottom 3 nodes in yellow, you can see that 46,000, 10,000, 8,000. So those people whose spouses are not too old or who are not married are not as rich as those people with older spouses. Okay, and married and older spouses. So I like to joke to students, you want to be rich, you marry your spouse. Of course, you have to be old enough to be rich. So this is how you would get a Y hat. So I use 2/3 of the data to build this. This is like a regression model. It's a step function, really, because it's average. Just cut it into regions. Out of 550 variables, so there's a lot of massive search going on. And then when you drop it down, you get a Y hat. So I get a Y hat for the 1/3 that are missing. I plug it into that formula. And And this is to estimate the propensity or the response. The state appears twice, and PSU is primary sampling unit. So apparently, somehow in the United States, people in some states are less willing to tell you how much interest and dividends they have compared to other states. So state is a big predictor. But what are the things in red? The things in red all involve missing values. And this makes sense. We're trying to predict the probability of missing value. So you should not be surprised that to predict whether Y has missing values or not, whether X1, X2 have missing values or not is a good predictor. But if you don't do this, what you do is you use logistic regression to predict this probability, right? Logistic regression will predict. That's the usual propensity score method. But to do that, your model, all the X's have to be imputed. Otherwise, how do you fit the logistic regression model? Now that you impute all the X's, right? Even when it's ridiculous to impute age of spouse, then you fit the logistic regression model, and from the pi, you use that for the inverse probability.
Why not use missing indicators?
You could, but then you only use missing indicator. You see, age of spouse has a lot of information, all the ages. You have the missing value indicator. But then what about the missing values in age of spouse itself? You have to impute something. Otherwise, you cannot use it. Right? So your model, you want to use age of spouse or X1. Then you have a missing value indicator 0, 1. Let's call it X1 prime. So you're suggesting we use both, which is a good idea. But to use both, X still has to be completed. Unless you only want to use X1 prime, which will throw away a lot of information. X1.
Use two missing data indicators.
Use two missing, like, what do you mean?
Well, I think I haven't followed your example exactly, but one of the things is age of spouse moving.
Yes.
The other thing that might be missing?
It's just a Y variable. We're trying to predict the probability that Y is missing or not missing. It's not X. So there's only, here we only have actually some of the other variables also have missing values. So you can pair each X with X prime.
That's what I'm suggesting, yeah.
But then your X, in order to use your X, what are you going to do with the missing values inside X?
Replace them, it doesn't really matter, does it?
That's an interesting question. If there's only one X with missing values, you have a lot of X values, right? You fit a logistic regression model or even linear regression. It turns out that your predicted values is invariant on what you impute for the missing value in X. But if you have more than one, then it's not invariant.
Okay.
Because it could be that, say, my age is missing, but my spouse age is not missing, or my age is not missing, my spouse age is missing, or both of us are missing. So there are all kinds of combinations. And that, what you impute for the missing values in the X variables will have an effect. Nobody knows what. Although if I were to do it, I would just impute the mean, pray for the best. Okay, so now this is the final estimate after we do that, the three methods. It's about $5,000. I also include the forest. Forest is a bunch of 500 trees. I don't have time to talk about that. So it looks pretty stable. So I have a few minutes. Maybe I can talk about a more recent project with the United States Department of Agriculture. They do a farm survey every year to figure out the health of farms in the United States. United States farm industry is very important. In fact, the government will subsidize farms if they make a loss. Just to make sure that farming goes on, right? So the Economic Research Service is an arm of the USDA, and they have a lot of missing data, and they asked me to help. So they want to know what is the total household income, what is the total household expenditure, assets, debts of each of the farm households in the survey. But like total debt, second bullet, total debt is composed of many components. Okay, mortgages on dwellings and real estate, and that's more than one mortgage. Just group them together. Personal and business loans, our farm debt. So actually that here at the bottom here, there's 5 components. Then expenditure has 16 components, income has 70. And there are a lot missing. So the moment one component is missing, they cannot calculate the total. So what they want, they don't ask for the total because it's too much for people to understand. They ask for components and then they do the addition themselves. But the moment one of the components is missing, they cannot calculate the total. So what they do currently is they don't use the components even if they have information. If any one of them is missing, they just impute the total. So they feel that there's a waste of data, right? So they ask me to help them impute the components so that they can do the addition, right? And so, well, this data set, are we running out of time? Okay, so what should I do?
Well, maybe move on to, if you've got a final slide with.
Okay, so I'll skip this example. This example has all kinds of integer coded ranges, which is not actual dollar values. I'm just going to skip that. Oh, before that, this Hippocratic oath, since you guys do it. You know, in medicine, we have a Hippocratic oath. It says, roughly saying, if you cannot help a patient, don't mess it up, right? But nowadays in machine learning, we should have a Hippocratic oath. Machine learning doesn't have this. People in machine learning mostly don't care whether they do harm to you or not, right? There's currently a lot of algorithms and there's a lot of research on fairness in AI. But fairness in AI is not about whether the algorithm is truthful. It's whether the data are fair. The training data, most of the talk is whether you use the right data, right? But I think that should be something about fairness in machine learning algorithms. So here is an example. So a lot of methods give you important scores. So here I have 12 methods. BART is a Bayesian card, then Forest, gradient boosting machine, GBM, there's guide, there's lasso, ranger, so many. Okay, they all can give you important scores. So these scores are plotted there. All right. So how did I get this picture? I just simulated some data, artificial data, where no X is predictive of Y. So I generate a bunch of random variables, X, and just a bunch of Y. They're totally uncorrelated. And then I do important scores. You'll find that if the method is unbiased, these are confidence intervals. They should all overlap. But look at random forest. Where's random forest? Random forest is here. Variables that are correlated are here. They suddenly become more important. Even though they're not important, we know that with the simulation, we made them not important. Okay, just by virtue of the fact whether they are continuous, whether they are correlated. These are the binary variables, categorical variables. This is what I mean by fairness. Okay. So very little is done. Nobody cares actually, because it's very hard. Actually, it's not so hard, but to ensure that you don't have this bias. You know, the algorithm should not have selection bias. So imagine the COVID data. Imagine hypothetically, we have 85,000 people, right? And suppose these 85,000 people all have different occupations. It's a massive categorical variable. They're all unique. The best predictor is occupation. All you have to do is look at the subset of all people who died. These are occupations that is 100% accuracy. You split on that, it's finished. 100% prediction. Because if you have so many categories, there's so many ways to purify the data. You can always find one that looks really good on the training data. Okay, so that's all I think I want to end with. I can also fit, but anyway, so these are some properties of guide. Sean was talking, I was talking with Sean about theorems. I didn't mention any theorems, but the theorems were proved a long time ago. In Bryman 84, my colleague and I, 1994, 95, we proved asymptotic consistency. Bryman proves that the CART method is asymptotically consistent in terms of base risk. My colleague and I prove it in terms of point-wise convergence, uniform over compact sets. So all the theory is there, but the theory is irrelevant because sample size never goes to infinity. But people who don't know about the whole history, they say all these machine learning methods don't have theory. No, the theory is really established. But they're very, they're necessary conditions to prove the consistency, obviously. Thank you.
Okay, thank you very much.